Welcome to the lecture on microstructural products in weldments. So, in the last lecture we talked about the properties of the heat affected zone, and in that lecture we typically talked about the changes in the mechanical properties, especially the hardness and the toughness, which is varying towards or along the subzones of the heat affected zone. So, and typically we talked about the effect of the grain growth, because below the fusion line and as we move toward the heat affected zone. So, heat affected zone. So, near that fusion line under bead zone. So, there you have the probability of having coarsening of the grains, and that affects the properties. Towards the later part we also discussed about the effects which are further to be kept into mind, like the material may subject to aging. So, as we know that aging is a typical type of heat treatment process, which is which normally we refer to the non-ferrous type of materials. However, steels also are subject to aging, and typically we talked about the natural aging behavior of the steels also. Similarly, for the austenitic stainless steels also, they also undergo the precipitation hardening, so that is through the formation of intermetallic phases, and that is possible with the presence of aluminum, titanium and phosphorus type of materials. So, even in the austenitic stainless steel, so they are also subjected to the precipitation hardening, and that is with the formation of intermetallic phases, and that is in the with materials like aluminum, titanium or phosphorus. So, these steels have corrosion resistance compared to other the stainless steels. So, they will be also they become normally brittle when they are exposed for many more hours at somewhat elevated temperature, like maybe close to 300 degrees centigrade. So, normally what we do is we normally limit their use to the lower temperature range. So, basically we try to keep the temperature, working temperature, somewhat smaller in those cases. Then another important property which has to be looked into is the strain age embrittlement. Now, this strain age embrittlement, it can be seen as the first step towards precipitation or aging treatment. So, as we have studied earlier that in the strain aging behavior, what happens that you strain and then further you reload, and then once it is heated to certain temperature, then in that case or it is left for some time, in that case reappearance of the yield point is phenomenon is observed that we had earlier discussed. So, strain age embrittlement is another possibility when we talk about these heat affected zone formation. So, it is the possibility when the metal has been strained and heated with to some temperature. So, it is basically when metal has been strained and heated within some temperature range. So, that range is about 100 to 300 degrees C. So, basically because of this there are this is associated with the formation of very fine precipitation. So, this is because of the fine precipitation, or you have the clustering of dislocation. So, that has been observed when there was microscopy done. So, that was seen that when you are heating to this smaller range, then this strain edge embrittlement is also observed. Now, normally the presence of nitrogen or even carbon that we have discussed, that is normally responsible for this strain edge embrittlement. So, nitrogen is and carbon also. So, nitrogen in carbon or carbon manganese steels. So, that is normally responsible for this strain edge embrittlement behavior. Then normally because of that the ductility is reduced. Now, what happens that the particles which are responsible, that is carbon nitrides or the nitrides. So, so basically this strain edge embrittlement is that way important to be kept in mind, because that you have to avoid the heating that process. Then another property which is another further important is the temper embrittlement. So, this is basically the because of the formation of unfavorable transformation products, and that is through the grain boundary segregation, and that is why in this case this is known as the temper embrittlement. So, this is again the by heating in the certain temperature range. So, if you have the if the holding is there in the temperature range of maybe 375 to 500 degrees centigrade. So, this is 575 degrees centigrade. So, this is basically the tempering temperature range as we all know. So, once you do the tempering in this range, in that case you have the formation of undesirable transformational products, and that is formed through the grain boundary through the grain boundary segregation, and that basically leads to the decrease in toughness or increase in the embrittlement. So, basically this is another treatment which is or this is another phenomena which occurs in the case of due to the thermal cycling treatment, because when you are heating then certain zone are heated to that temperature zone, and then there is further cooling. So, that may lead to these temper embrittlement conditions. So, basically plain carbon steels are highly susceptible to this temper embrittlement, and but if you add 0.5% of molybdenum, it will reduce this tendency. And there are certain elements also that increase also the tendency. So, that is like antimony, tin, phosphorus, these elements are basically they will be increasing the degree of embrittlement. So, then there are also elements which will be increasing that susceptibility that is to smaller extent, like manganese, vanadium or boron. So, that way your this type of observation is there in the in certain type of steels. Now, for finding this how much susceptible it is to the temper embrittlement, for that there is a parameter, that is J factor So, that J factor basically is calculated. So, this J factor calculation is based on the value of the alloying elements which are there, and J factor is basically calculated. So, this J will be calculated as manganese plus silicon, and then multiplied by phosphorus plus tin, and then this will be multiplied with 10 raised to the power 4. So, basically what happens that you have a graph, and that graph has on the abscissa you have J factor. So, that J value is there, and then you have the fracture appearance transition temperature, that is also there So, for that the plot is drawn, and accordingly you can see that what way this material will be susceptible towards the temper brittlement. Now, it is normally very much important when we talk about the vessels in the nuclear power or the petrochemical plants, because in those cases the fracture toughness for ascertaining that fracture toughness values. So, in that case this J factor this parameter is important. So, there it is normally required. So, when we have to design the vessel which is going to be used in the nuclear powers or in the petrochemical sectors, at that time you need to deal with these terminologies. Then the further the another terminology which will be important will be the graphitization. So, what happens, as you know, that in many cases the carbon may be converted towards the graphite. So, we get carbon in different form, we get carbon in combined form, we get carbon in cementite, we get carbon in graphite. So, basically when you have the non-corrosive environment, now in that case the steel welds may lose the strength, that is due to the phenomenon called graphitization. So, if the steel will be held at some temperature, maybe something like maybe more than 450 degrees centigrade, for that for long periods of time, then cementite will be decomposed. So, cementite decomposition to graphite. So, cementite decomposition to graphite will lead to basically the decrease in the strength of the weld, and so, and what happens that you are ending up with the formation of the graphite globules in the low carbon matrix. So, low carbon iron matrix. So, basically the breakdown of this cementite to graphite, it is basically it will be promoted by the addition of aluminum to steel. So, we many times we add aluminum to the steel, and the carbon and as well as carbon and half molybdenum steels, they are very much susceptible to this defect known as graphitization. So, basically what happens, you have on the grains you have the grain boundary. So, there will be grain boundary carbides formed. So, this way you will have the grain boundary carbide formations along the grain boundaries. So, what you see that in this way you have these are the grain boundary carbides. So, these this will be because of the holding of the steel more than at about more than 450 degrees centigrade for basically for higher time. So, that leads to these eyebrow type of graphite eyebrow type of structures, this is what you get in that heat affected zone. So, now what happens that basically chrome moly steels normally will not be affected I mean in the sense that the graphitization does not occur in the case of chrome moly steels, because in the case of chrome moly steels the carbides in these cases carbides are more stable. So, in these cases they are not basically affected because of affected because this by the presence of these globules of these graphite. So, this way the your structures are also changed. So, what we see that the welding processes basically lead to the development of different microstructural products in the weld metal and the heat affected zone. So, as we have seen that as it is subjected to different types of thermal cycling. So, you have the production of different type of microstructural products, and these mechanical properties of the weldment will be depending upon the type of microstructural products in the weld metal and the HAZ. So, you have different basic constituents they are which are there, phases are formed in the HAZ and the weld metal zone. So, the different constituents which are formed are many, and normally your two basic constituents which are formed are the ferrite and the cementite. So, if you talk about the basic constituents, so we know that you have the presence of ferrite, and as we know that ferrite is in the form of or it is also known as the alpha iron. So, this is the almost pure iron which is formed which is there in its case, and carbon can be dissolved to form the solid solution ferrite in this case, and you have very less solubility of carbon in the alpha ferrite at room temperature, and it goes to very smaller value like 0.006%. Its solubility is there at the room temperature, and it will be increasing as the temperature is increased. So, at if you go to 750 degrees centigrade, that is once you go to that horizontal line of lower critical temperature. So, around that it will be going to somewhere close to 0.05 percent. But ferrite has the capability that it can dissolve a large number of second elements other than carbon to form the alpha solid solutions. So, that way many alloying elements which we talk or second particles which are there, they can be easily absorbed by the ferrite. So, if you look at the ferrite structure, if you look at the weldment structure, then you can easily recognize ferrite. So, for that we normally etch with suitable reagent like nitrile. So, what you see is that ferrite can be seen as the polyhedral grains, and they are normally regular in shape and size, and it is normally soft, weak and ductile, and also it is magnetic up to the Curie point of iron, that is about 770 degrees centigrade. Up to that the ferrite is magnetic. Now, the next basic constituent is your cementite. So, cementite, as you know, this is its composition or the formula we write it as the Fe3C. So, it is basically the chemical compound of iron and carbon, and as we know that this is a compound of iron and carbon, and we know that it has about carbon is about 6.67%, and it is formed at about 1500 degree centigrade, and it is the hardest constituent found in the iron carbon alloys. So, it is extremely hard. Now, it can also dissolve a wide variety of elements like manganese and chromium. So, that way it can you can have the complex carbides. This cementite is basically losing its magnetism at about 210 degrees C. So, and it is hard and brittle. Now, the cementite are basically present, they can be present as free cementite, or it will be, or it can be laminated with ferrite. That structure we know that is formed at a certain reaction, invariant reaction, we know that eutectoid reaction. So, there so that in that you have lamellar structure of ferrite and cementite. So, that way, so there it is known as the perlite. So, you have a free cementite, and you have the laminated structures, that is your combined structure, that is your, so not combined. So, this is your perlite or laminated structure. Now, if you talk about the free cementite, now free cementite also are of two types. So, free cementite will be either so free cementite may be either it may be primary cementite or it may be secondary cementite. So, when we talk about the primary cementite, so this primary cementite is basically solidifying directly from the melt. So, and they will be occurring in the form of hard needles. So, that is your primary cementite, and you will have a needle type of a structure that can be seen in those cases. Now, the secondary cementite, so that is that precipitates in the solid. So, at low carbon content, the secondary cementite is formed, and that is formed at about lower critical temperature, that is your A1, and it will be occurring along the ferrite grain boundaries. So, along the grain boundaries you have the formation of that secondary cementite which is formed, and it is normally this type of cementite, that is secondary cementite, this is encountered in the weld metal which has very low carbon content. So, in those cases you have the possibility of formation of the secondary cementite. You also have another cementite, that is your pro-eutectoid cementite. So, before the eutectoid temperature. So, again that also is in its forms in the solid state. So, you have that is pro-eutectoid cementite. So, it will be precipitated from the supersaturated solid state austenite, and that way. So, it will be, and at eutectoid point it will be giving you the perlite, completely perlite structure. So, before that from austenite it will be formed. So, although these ferrite and cementite, these are the two basic constituents which have been cited, but depending upon the composition and the cooling rate, I mean that or the post weld heat treatment which we apply, there are different allotropic forms, they exist in different allotropic forms and morphologies. So, accordingly they will be influencing that mechanical behavior of the material. So, depending upon the different microstructural phase encountered which is there in the welding, the steel are basically are grouped into so microstructure is grouped into 3 categories again. So you have the primary microstructure, you have secondary microstructure, and you have tertiary microstructure. And you have tertiary structure. So, if you talk about the primary structure, this is obtained by the direct solidification of the molten metal, and it will be usually resulting in the cast structure. So, that is your primary structure. So, as you know, in this case you will have the development in terms of the columnar grains, and they will be parallel to the direction of the heat flow or the temperature gradient, as we have discussed about the formation of these grains and growth of these grains in the direction opposite to the parallel direction of the heat flow. So, they are parallel directions basically, and you can also have sometimes the formation of dendritic substructures inside the columnar grains, and this is normally found in metals without these phase transformation in the solid state, like in aluminum. Primary structure is usually retained on cooling to the room temperatures, although there may be changes in the substructures upon the cooling. Now, two major basically primary microstructural products are which are seen in the case of steel welds, that is alpha or delta ferrite as well as the austenite gamma iron. So, that is normally there in the case of steel welds, that is your delta ferrite and the gamma ferrite. Then if you come to the secondary microstructure, so that is formed because of the transformation of solid phase austenite. So, this is because of the transformation of solid phase austenite. Okay, so it will be transforming into different solid phases. So, different solid phases may be like you have the perlite, you have benite, you have martensite. So, then you have grain boundary ferrite, you have ferrite side plates and all that. So, transformation of this solid phase austenite into all these different constituents, that is the secondary microstructure. And if you talk about so basically you will have different degree of fineness, and that will be affecting the mechanical properties of the material. And if you talk about the secondary microstructure, so the secondary microstructure is or tertiary microstructure, so that is encountered in normally multi-run welds. So, encountered in multi-run welds. So, what happens that you have one first run and second run, and that way you have successive run of welds is run weld is going on. So, because of that the previous run which of the weld which is there, it is further heated to the austenitic zone, and then you have the product of different fineness that will be formed, and that will be affecting the properties of the material. So, that is because of the normalizing effects, because the product which has been there, so that is further subjected to some treatment. So, that way you have different types of structures of different fineness and different properties are formed. So, apart from that You have also different as we talked, you have the formation of the delta ferrite or austenite, which is there a part of the secondary structure, and we need to understand the formation of these, or we need to be conversant with these phases which are formed in weld, because these phases by looking at the structure or microstructure, you can have the analysis and you can do the proper justification for with regard to the properties of the materials. So, this is about the different structures which are observed in the case of welding. Thank you very much.